2,500 years ago, Democritus said, "Sweetness and bitterness, warmth, cold, and color are only appearances. In truth, nothing exists but atoms and the void." Ever since the beginning of history, lonely men have searched for a pot of gold under a distant rainbow. Now the prospector has become, in a sense, a scientist. Now the object of the search is not only gold, silver, and copper, but also uranium, a radioactive metal which signifies its presence by the reading on a Geiger counter. Scientists foresee that in future years, uranium may supply power to heat our homes, drive our cities, an engineer's dream, a future reality. Today, blueprints for atomic power will require years to develop and apply. But atomic energy has still another aspect. The nuclear reactor, incubator of plutonium, precursor of the atomic power plant of the future, is also the source of radioactive materials known as radioisotopes, available now as peacetime weapons in the continuing struggle for health, material satisfactions, and scientific progress. The radioisotope is probably the most important new means of perception and investigation since the invention of the microscope. To use this new means of perception, the scientist has been forced to acquire many novel techniques, absorb a variety of concepts unfamiliar to him. The radioisotope becomes useful to the scientist only when these concepts have taken their places in an orderly structure of method and underlying theory. The first concepts the scientist faces are those which have to do with the nature of matter and the dynamics of its smaller components. Now, it is known that the atom, long considered the basic unit of matter, is itself a void, in which planetary particles called electrons revolve in great orbits around a central nucleus. The nucleus also has a structure. It is composed of protons and neutrons. Each proton has a weight of 1.00758 atomic mass units. The neutron is slightly heavier. In the usual notation, the mass is shown in round numbers, 1 for both proton and neutron. The proton carries 1 unit of positive charge, indicated in subscript. The neutron has no charge. The electron has 1 unit of negative charge. Its mass is insignificant compared to that of a proton or neutron. Again, charge is shown in subscript, mass in superscript. In describing an atom, the same notation is followed. The atomic number of the element, in subscript, is equal to the number of electrical charges carried by the protons in the nucleus. The mass number, in superscript, is equal to the sum of protons and neutrons. For instance, the designation for helium is 2 helium-4. Normally, the positive charge of the 2 protons in the nucleus is balanced by the negative charges of an equal number of orbital electrons. Atoms can be classified according to the number of protons in the nucleus, or the atomic number, and according to the number of neutrons. In terms of proton number and neutron number, it is possible to define any atom. Normal hydrogen atoms, for instance, have 1 proton and no neutrons. Helium, with 2 protons, usually has 2 neutrons. Lithium most often has 3 protons and 4 neutrons, and so forth. All the other atoms are identified according to the same system. The number of protons, or the atomic number, identifies the element. All atoms of the same element have the same number of protons. However, in most elements, there are found atoms of different neutron numbers. These different forms of the same element are isotopes, atoms of the same element, alike chemically, differing only in the number of neutrons. The sum of protons and neutrons gives the mass number. For instance, an atom of helium, which has 2 protons and 2 neutrons, has a mass of 4. A lithium atom with 3 protons and 3 neutrons has 6 mass units, and so on. Different isotopes of the same element have different mass numbers, since they have a different number of neutrons. Again, to complete the description of each atom, the element is accompanied by its atomic number in subscript. Most elements have 2 or more isotopes. However, a few have only 1. For instance, cobalt, element number 27, has only 1 natural isotope. All cobalt atoms found in nature have the same atomic weight, 59, and therefore the same number of neutrons. However, most elements have more than 1 natural form. For instance, zinc, number 30 on the chart, has 5 natural isotopes. In zinc, as in most elements, the number of neutrons is greater than the number of protons. The number of neutrons can be found by subtracting the proton number from the mass number. Higher on the chart, a few additional elements have only 1 isotope, though most have several. At higher atomic numbers, the ratio of neutrons to protons becomes greater and greater. In the natural isotopes of mercury, for instance, the lightest atoms have 116 neutrons, 36 more neutrons than protons. The heaviest have 124 neutrons, 44 more neutrons than protons. To illustrate neutron-proton ratio, the isotopes can be plotted on a graph of atomic number against neutron number. In this graph, a straight diagonal line would intersect all points at which proton number equals neutron number. However, if the isotopes found in nature are plotted on such a graph, it is found that they depart from the diagonal. In other words, they have a preponderance of neutrons over protons, a preponderance which tends to increase at higher atomic numbers. With a few exceptions, these positions represent atoms with stable neutron-proton ratios, capable of existing indefinitely without any observable change. The empty spaces represent neutron-proton ratios which would not be stable. It is reasonable to assume that if an atom existed in an empty space on the chart, it would show a tendency to change itself to an atom having a more stable neutron-proton ratio. For instance, an atom occupying a position above the natural isotopes would have a disproportionately high ratio of protons to neutrons, and would tend toward the position of one of the naturally stable isotopes below it. Similarly, an atom having a disproportionate excess of neutrons over protons would tend to take a position of one of the naturally stable isotopes above it. This illustrates one of the primary principles of nuclear stability, the tendency of all atoms to reach an equilibrium in terms of a stable neutron-proton ratio. Up to atomic number 83, the natural isotopes are stable, with a few exceptions. However, above atomic number 83, all the isotopes are unstable. They all have a disproportionate number of neutrons, either too many or too few. Without exception, these isotopes are radioactive and return to stability through a process known as radioactive decay. For example, uranium, the heaviest element found in nature in significant amounts, has 3 natural isotopes. Each uranium isotope tends to return to stability through a series of transformations ending in a stable form of lead. An example of this process is the way in which uranium-238 changes to lead-206. The transformation from instability to stability is a complex process which takes place in a series of separate steps. The first step occurs when the uranium atom throws off a nuclear particle of 4 mass units composed of 2 protons and 2 neutrons. This single unit is known as an alpha particle. With this change, the uranium-238 atom becomes thorium-234, which has 2 less units of charge on the nucleus and 4 less units of mass. The nucleus of the thorium atom emits an electron which possesses a negative unit of charge and negligible mass. This electron, thrown off by the nucleus of the thorium atom, is known as a beta particle and is usually represented by the Greek letter beta. With this emission of a negatively charged beta particle, thorium-234 in turn changes to protoactinium-234, an atom with 91 charges instead of 90 on the nucleus. Protoactinium-234 throws off a beta particle, increasing atomic number by 1, thus changing to uranium-234. Uranium-234 next throws off an alpha particle to become thorium-230. In successive transformations, further alpha particles are given off, resulting in radium-226, radon-222, polonium-218, and finally lead-214, an unstable isotope. 2 beta particles are emitted successively, producing bismuth-214 and polonium-214. Polonium-214 gives off another alpha particle to produce lead-210, still unstable. Again, 1 beta particle is emitted in each of 2 changes, to form polonium-210. With the emission of a final alpha particle, polonium-210 goes to lead-206, a stable isotope. Thus, in radioactive decay, a complex series of nuclear transformations has taken place from an unstable neutron-proton ratio to a stable state. In every step of radioactive decay, the transformation is from parent to daughter, and parent to daughter. Atoms of the parent element decaying to produce atoms of a daughter element. The same terminology applies whether or not the transformation is to a higher or lower atomic number. There is no way of foretelling when any particular unstable nucleus will decay from one step to the next. However, in any sample of a radioactive isotope having millions of billions of atoms, some of the atoms are always in the process of decay. The number of atoms decaying in a unit time in a sample of radioactive isotope is called the activity of that sample. Activity, or rate of decay, is generally stated in terms of millicuries, or MC for short. A given sample of radioactive material is said to have an activity of 1 millicurie when 37 million atoms decay or disintegrate per second. The millicurie is the commonly accepted measure of radioactivity. Decay from a parent isotope to a daughter isotope can therefore be illustrated in terms of the number of unstable atoms and the time. On this graph, the number of unstable parent atoms that exist at any given instant can be represented by a point. Since the parent substance is decaying, Fewer unstable parent atoms will be present at any later time. In the language of simple calculus, the number of parent atoms has decreased by delta n during a time interval delta t. The slope of the line between the 2 points corresponds to the rate of decay. The rate of decay, delta n over delta t, is proportional to n, the number of parent atoms present, or equal to minus lambda n. The minus sign indicates that n decreases with time. Lambda is called the decay constant and is characteristic of the particular parent radioisotope. If decay is plotted as a continuous series of short time intervals, an exponential formula is derived, which is the basic standard formula for radioactive decay. In this formula, n is the number of radioactive parent atoms present at a given time. N sub 0 is the number of radioactive parent atoms at the beginning of the first time interval. E is the base of the natural logarithms. Lambda, of course, is the decay constant of the parent substance. Since the number is proportional to the activity, the symbol n can be replaced by a throughout the formula. Accordingly, the same curve can equally well represent the change of activity, rather than number, versus time. From this equation for radioactive decay, activity at any moment can be determined in terms of the initial activity. In any decay process, there is a point in time at which activity is equal to 1/2 of that present initially. This time during which activity has decreased by half is known as the half-life. In successive half-lives, activity continues to decrease by successive halves, until finally only a small fraction of the original activity remains. Since the decay rate for a specific radioisotope is usually given in terms of half-life, it is often convenient to substitute half-life for the decay constant lambda. The equivalent of lambda is 0.693 divided by half-life. This formula is often used in finding activity at any time t when half-life is known. Plotted in terms of the logarithm of activity against time, exponential decay is shown as a straight line. Figures for half-life are generally available in isotope literature. Each radioisotope has a specific half-life. The half-life may vary greatly, from a fraction of a second to thousands or billions of years. For instance, one isotope of cadmium has a half-life of 2.3 days. While carbon-14 decays to its daughter nitrogen after a half-life of roughly 5,700 years. Or take the case of uranium. U-238 has a half-life of 4.5 billion years, giving a straight line on a graph calibrated in terms of days or weeks. In contrast to the long half-life of U-238, thorium-234, the daughter of U-238, has a half-life of 24.1 days. Thus, while all steps of decay are unpredictable in a single atom, the statistical rate of decay in a large number of atoms can be predicted and measured with great accuracy. Examining the various steps in the decay series beginning with U-238, it appears that there are at least 2 ways in which unstable atoms can change to a more stable form. By throwing off an alpha particle and losing 4 units of mass and 2 electrical charges, or by throwing off a beta particle and increasing atomic number by 1. In the process of decay of U-238 to stable lead, Each of the two types of transformation occurs several times. In 8 steps of decay, 8 alpha particles are given off. 6 beta particles are emitted. One would assume that these 14 particles would account for the mass difference between uranium-238 and lead-206. Let's check this assumption. The exact weight of an alpha particle is known from accurate determinations. The 8 alpha particles thrown off weigh 32.022 units of mass. The mass of beta particles is also known with great accuracy. Adding the weights, it is found that 32.025 units of total mass have been given off as discrete particles during the decay process. But if the weight of lead-206 is subtracted from that of uranium-238, we find that the total mass lost in the decay is somewhat greater than that represented by the alpha and beta particles thrown off. In other words, 0.045 units of mass are unaccounted for, representing a minute fraction of a gram. According to Einstein's formula, energy and mass are equivalent. Substituting and solving the formula, it is found that this mass represents a really significant energy. In the transition from uranium to lead, this energy has been released in addition to the alpha and beta particles emitted. Most of this energy, released during uranium decay, has been applied in giving the ejected particles their high speed, in other words, as kinetic energy. Additional energy is also released as a form of electromagnetic energy known as gamma radiation. To summarize, the decay of uranium-238, resulting in stable lead, is accompanied by the release of alpha particles, beta particles, and gamma radiation. This is generally true. A change from instability to stability is accompanied by energy released as discrete particles or electromagnetic radiations, or both. It is the energy released by the decay of uranium in uranium-bearing ore which makes it possible to detect it with a Geiger counter, even though mixed in minute proportions with a variety of other substances. The decay series, beginning with uranium-238, is only one of several. A similar decay scheme begins with U-235, another with thorium-230, another with thorium-232. Uranium and all the unstable elements near it on the chart have very long half-lives, which have permitted them to survive from an early age of greater radioactivity. They are fated by the inevitable process of decay to return in time to a stable state. Lower on the scale of elements are found a few unstable survivors, naturally radioactive isotopes of long half-life, such as rhenium-187, lutetium-176, tin-124, rubidium-87, and potassium-40. All of these return to stability in a single step. Potassium-40 offers a good illustration of the 3 possible modes of nuclear transformation. As one possibility, potassium-40 may give off a beta particle, increasing its nuclear charge by 1 and changing to calcium-40. In this case, the beta particle is accompanied by excess energy as a gamma ray. Or potassium-40 might emit a positive electron, reducing atomic number to become argon-40. The positive electron is known as a positron. As the third possibility, the potassium nucleus may absorb an electron, becoming argon-40 without emitting any discrete particle. In all 3 cases, there is a change in atomic number without any significant change in mass. The sum of neutrons plus protons remains the same. Obviously, each change must involve a shift in the neutron-proton ratio in the nucleus. For example, when potassium-40 changes to calcium-40, one of the neutrons in its nucleus has become a proton and an electron. In other words, a neutron of 0 charge and 1 mass unit has become a proton of positive charge and mass 1, and an electron of 1 negative charge and very slight mass. Mass and charge units are conserved in the transition. When potassium-40 emits a positron and changes to argon-40, a proton in the nucleus has changed to form a neutron and a positron. This type of nuclear change is called positron decay. In the third possibility, one of the protons in the nucleus may join with an electron to form a neutron. This transformation would seem contrary to logic, since it is generally assumed that there are no free electrons in the nucleus. Such a phenomenon can best be explained by referring to the nucleus and its surrounding electrons. It sometimes occurs that an electron from the inner or K shell is captured by the nucleus and is immediately absorbed by a proton. The opposite electrical charges neutralize one another, and the proton becomes a neutron. This transformation is known as K-electron capture. When it occurs, it causes a series of changes in the outer electron shells. First, the empty space in the K orbit is filled by an electron from an outer orbit. The empty space in the second orbit is filled by an electron from an orbit further out, and so forth. In this cascade of electrons from outer to inner orbits, X-rays are released, which represent the difference in potential energy between different electron shells of the daughter atom. The K X-ray, which corresponds to the energy released in capture of the K electron, represents most of the measurable energy released. Thus, when potassium-40 captures a K electron and changes to argon-40, the transformation is accompanied by the emission of X radiation. While a single atom of potassium-40 can decay in only one of 3 ways, with a large number of potassium-40 atoms present, some will decay in each way. Energy is released as positrons, beta particles, and gamma rays, and in K capture as X-rays. In potassium-40 decay, positron emission is difficult to substantiate, occurring rarely, if at all. In K capture, the X-rays emitted are of low energy and difficult to measure. In other radioisotopes, any of these radiations may be given off in different proportions and relative energies. Decay and emission of energy as radiation occurs in all radioisotopes. However, uranium-235 and 1 or 2 other radioisotopes have a second and unique characteristic. If it were possible to observe a single atom of uranium-235 and to penetrate through the electron shells to the nucleus itself, it would appear to be in a constant state of agitation. probability, it would throw off an alpha particle as the first step in the decay process. However, in a gram of U-235 in each second, at least one atom behaves quite differently. It becomes more and more unstable until it splits into two fragments, each a lighter atom of lower atomic number. In addition, two or more neutrons are left over from the reaction. This is the reaction of spontaneous fission. In a single fission, taking place in a minute fraction of a second, considerable energy is released, about 4 times as much as in all steps of the long decay process of U-238 to stable lead. Part of the energy is kinetic energy, giving velocity to the neutrons in the two fragments of uranium. The remainder of the energy is given off as gamma radiation and beta radiation. In uranium fission, 1 to 3 neutrons are emitted. If enough uranium atoms are present, one of the neutrons may strike and be absorbed by another nucleus of U-235. With the added mass, this nucleus in turn fissions, releasing still other neutrons, and the process continues. This is a chain reaction, such as that which takes place in an uncontrolled manner in the atomic bomb. However, if uranium fission occurs in uranium mixed with some light substance, such as graphite, the neutrons are slowed down by collision with the carbon atoms. Because of its slowing action on the neutrons, the graphite or other light substance is known as a moderator. The neutrons, because of their reduced velocity, are much less likely to escape from the uranium and are much more likely to penetrate to the nuclei of the uranium atoms. If the amount of uranium and moderator is too small, a large proportion of the neutrons will escape, and the reaction will die out. If the structure of moderator and uranium is larger than a certain critical size, the reaction will sustain itself.